Hi. So the objective of this video is to discuss transformers when we look at circuitry. And the motivation for this for the MEMS class that I'm currently teaching is to understand how to deal with an ideal transformer as we'll ultimately apply that to lumped element modeling. So let's go ahead and first just look at a transformer in general. A transformer is made up of two inductors where the voltage and current on one side of the circuit interact and are coupled with the voltage and current on the other side of the circuit. So in this picture here, the notation that I use is that going into the first transformer, I have some current that I will call I1. And anytime I'm referencing something that is associated with the transformer, because if you have a big circuit, there's lots of voltage drops, there's lots of currents going everywhere. Specifically for a transformer, I like to include a little star variable, so I know that I'm referring to the transformer. Additionally, the voltage drop across that transformer, I will say is V1 star. On the other side, I will go ahead and have the same type of thing, but I will say that it is V2 star and it is I2 star. Now, the relationship between the voltages and the currents depends on, in real life, how the inductors are set up, how many coils it has, the material of what the coil is wrapped around, things along those lines. For our purposes, we're going to combine all that, because again, just for modeling purposes, into something called the turns ratio, which is the Greek letter phi. And we typically write that as a ratio where we have 1 to phi or phi to 1 or something along those lines. Now, there's a few interesting things to note about this setup. First off, the power in the left circuit must equal the power in the right circuit. And again, we're assuming this is an ideal system without any losses. The power in the left circuit, if you think about power from your Physics 2 course or your electricity type of course, your circuits course, is the product of voltage and current. That is the product of them. Now, does that mean that the voltage V1 star is exactly equal to V2 star and the current I1 star is exactly equal to I2 star? Not necessarily. It depends what this turns ratio, this phi, is. So the thing that we need to remember when we're looking at this is that the voltages are related to each other using this ratio. So if I were to write, let me move this out of the way. If I were to write that the ratio of V1 star to V2 star, I want to set that equal to something involving the turns ratio. In this example, I have it written as 1 to phi. And the way that I typically remember this is that literally this 1 is closer to the V1 and the phi is closer to the V2. So I will make sure that if I put V1 star in the numerator, I will put the number that it is closer to also in the numerator. And if we arrange this, we see that if we cross multiply, we see that V2 star, I'll do it in blue, V2 star, that is equal to phi times V1 star in this example. because the turns ratio phi is set up in this proportion 1 to phi. Now, if we assume for a second that phi is bigger than 1, that means that the voltage in the right circuit, V2 star, is larger. We've taken V1 star and we have increased it into V2 star. Now, with that concept in mind, if I look at power conservation, how does this go up? And what do we have to account for with the currents? Because I need this product to be the same. I1 star V1 star is equal to I2 star V2 star. If V2 star goes up, what has to happen to I2 star? Well, I2 star has to go down. And we can prove this a few different ways. We can take that power conservation equation and what I'll do is I will substitute in what V2 star is into there. That is phi times V1 star. And again, this thing here, this is V2 star. We just plugged it in from the definition we had before based on the turns ratio. So if you look at this, you see that the V1 stars cancel. And we can write that I1 star equals I2 star times phi. And if I want to write it in the same way with where I'm solving for the second electrical variable, I'll divide by phi, and I'll ultimately get that I2 star is equal to I1 star over phi. So if you compare, try to get my colors right. If you compare this equation with this equation, we see that V2 star has been increased, or V1 star has been multiplied by phi to give us a larger voltage on the right side of the circuit, while I2 star is going to be smaller than I1 star. The current must have decreased because, again, we need to make sure that power conservation holds. So a really simple example, if I'm just doing this from a very basic perspective, is to say that if I have, oops, that's my really bad transformer. If I were to say that this is 5 volts here, and I have 1 amp traveling through, and I have I2 star in the other circuit, and V2 star also in the other circuit, and I tell you that the ratio between them is 1 to 2, I want to find both V2 star and I2 star. So based on our definition that relates the voltages, I will say that 5 volts to V2 star, maybe I'll just do 5, I'll drop the V. 5 volts to V2 star, that has to be equal to, the 1 is literally and physically closer to the 5, so I'll put that in the numerator, 1 to 2, which means that V2 star is equal to 10. So we see that in our circuit, we've gone from 5 volts to 10 volts. We have doubled our voltage. With that logic, what must I2 star be to ensure that we conserve power? Because if I look at the power in the first one, that's 5 times 1, that's V times I. This is 5. That has to be equal to V2 star, I2 star. Well, if V2 star was doubled, I2 star must be half of what I1 star is. And we can show this because we just found V2 star. That was 10. we get that I2 star is equal to a half. Now, the thing that gets a little bit more tricky, maybe I'll do it now. I was going to make a separate video, but this is fine. The thing that gets a little bit more tricky is when you start dealing with impedances. So if you have a circuit, let's say, right, provide some voltage input, and I have my transformer, and let's say on the other side of the transformer, I have some impedance that I'll call Z. Maybe it's a resistor, a capacitor, maybe it's a whole network of capacitors, inductors, whatever, that you can combine to an equivalent impedance. And I tell you that this ratio here is 1 to phi. How can we look at this in such a way to make it one overall circuit? Because right now we have something on the left that interacts with something on the right, but they're not actually touching, it looks like, based on the way that we drew it. So is there a way, can we combine the circuits in such a way? Well, first off, let's look at our transformer variables. We have I1 star here, and then we have the voltage drop across the transformer, that's V1 star. And then, of course, on the other side, we have V2 star and I2 star. And note in all these problems, I'll say that this is grounded at the bottom. So the thing that's really important is that if you were to just look at the left circuit on its own, let's ignore the right circuit. I'm just going to erase it for a second. We'll undo it. I'm just going to erase it. Let's just say it's that. Looking at this, it seems that you have this current I1 star that's traveling through an inductor, which has some impedance. And then that's it. That's the whole circuit. But the thing that's important is that because this inductor is coupled, the impedance that the left circuit is seeing also includes everything on the right side of the circuit. So this Z that is over here, even though it's on the right, is being experienced by the left circuit. That's a really important point. Its presence will impact the left circuit. So the question is how? Well, what I will do, I'm going to call this, instead of Z, I'm going to call this Z right, basically to say that it's on the right side of the circuit. And let's first see how we can relate Z right to some of the variables that we have. If V2 star is the voltage at the transformer, maybe we can think of that kind of like a source. And it's creating this I2 star that goes through the right impedance. Why can't I write something like V2 star is equal to I2 star times Z right? Which basically is saying that Z right, that is the same as V2 star over I2 star. That is the impedance as it currently is. The voltage on the right and the current on the right, the combination of them through Ohm's law will tell us what the impedance is. But what I would like to do, to transform Z right over to Z left. Basically meaning that I will have the same circuit, but in place of the transformer, I will just have the impedance, Z left, on that side. Now, because before, like I said, this whole thing kind of encapsulates everything that's happening on the right, the voltage drop across this is still V1 star, and the current that's traveling through this is still I1 star. So if we think about it like that, we can define Z left in the same exact way. Z left will be V1 star over I1 star. So if I can express Z left in terms of Z right, maybe that means I can transform it over. So how do you think we do that? Let's go ahead and look at what Z right and Z left are and maybe try to leverage our transducer or our transformer equations that can help us. So first off, we know, based on the way I drew this, let me erase the red, that V1 star over V2 star has to be the same as 1 over phi. What that means is that V2 star, V2 star, that is equal to phi times V1 star. And we also know, based on what we talked about before, that I2 star has to be I1 star divided by phi for power conservation. We said that before. So I would like an expression for Z left in terms of Z right. So maybe what I'll do is I will try to solve for V1 star and I1 star and then plug it in terms of V2 and I2, because then I can use this definition up here to replace that. So from this equation here, I know that V1 star, that is equal to V2 star divided by phi. And this equation here says that I1 star, that's equal to I2 star times phi. So we just found V1 star and I1 star. Let's plug them in to Z left. Z left, we just said above, was V1 star, which is V2 star over phi divided by I1 star, which is I2 star times phi. Now, if we simplify this algebraically with the fractions, we get V2 star over I2 star times 1 over phi squared. Those phis don't cancel. If you were to divide fractions the long way, like keep, change, flip type of thing, you'll see that that phi ends up, both those phis end up in the denominator. And the question is, what is this? This is Z right. So Z left will end up being Z right divided by phi squared. Note, this is only valid in this case where this turns ratio was 1 to phi. If it was phi to 1 or some other random thing, it might end up being that Z left is Z squared multiplied by phi squared. Z left is Z right multiplied by phi squared. I want to make sure I said that correctly. I might have stumbled some words there. Z left is equal to Z right times phi squared in that situation. But in this situation, we end up seeing that Z right ends up being divided by phi squared to bring it over. So let's do one example. Let's say I give you a circuit where I have, let's say I have some 12 volt signal. We'll assume it's sinusoidal just because sometimes, or rather the inductor won't really work if it's not sinusoidal in real life. And we'll try to maintain that with our model. And now my camera's not working. And now it's working. We'll say that this is 4 ohms. This is 1 to 2 in this example. And I say that this voltage across this second resistor, which is 6 ohms, this one is 2 ohms. I want to know what is V out. That's what I am interested in finding. So what could be our game plan here? Well, if we were to find, let's say we were to find V2 star, we know that V out will be some proportion of V2 star based on the fact that with each impedance, the 2 ohm and the 6 ohm, we are dropping some voltage amount, and by the time we go around the loop, we have to expend all of that voltage. That's based on Kirchhoff's voltage law. So if we're able to find V2 star, then we can find V out. But how do we find V2 star? What we would like to do is maybe try to find V1 star somehow. And unfortunately, because this resistor is here, we can't say that V1 star is equal to 12 or something like that. There's too many impedances in the way. So what we'll try to do is we will try to transform over the right impedance to the left. We'll do that first, and after doing that, we'll be able to find V1 star. So the impedance on the left, no, sorry, not the left, the impedance on the right, which I want to transform over, is the series combination of 2 ohms and 6 ohms. That will end up being just the addition of the impedances. So Z right is 8 ohms. And again, if I were to redraw that, it's now 8 ohms, and everything else is the same. So I want to transform this impedance over to the other side. And we just discussed how to do that before. We derived this for the ratio 1 to phi. And in this problem, we wrote it as 1 to 2. That means that Z right, that Z left, I'm confusing my rights and lefts. It'll be Z right divided by phi squared. And in this example, phi is equal to 2 based on that 2. So Z right will be 8 divided by 2 squared. This is 8 divided by 4. Therefore, that Z left is going to be equal to 2 ohms. So what I'm going to do now is I'm going to replace this whole thing with just a 2 ohm resistor. So this is 4, this is 2, and this is 12. The voltage drop across the 2 ohm resistor is V1 star. And the current that's flowing through it is I1 star. We'll see that. I don't really care about the current in this problem. You could use the current if you wanted to, but this is probably good enough. So if I want to find the voltage drop across the 2 ohm resistor, I could do voltage division. But we'll say that V1 star, that will be equal to our Vn. And then we'll have our impedance that we're interested with for the voltage drop, which would be 2 in this case, over the sum of the impedances that are in that circuit. And again, I can make this in a more general sense if I wanted to, just for the sake of explaining. Maybe I call this R4, or I'll call it R1, and I'll call this other one R2. This is more familiar with maybe what you've seen in your classes. This will be R2 over R1 plus R2. That's our voltage division. I'm hoping that that is more review, if anything. So this basically says that V1 star, this will be the same as Vn times 2 over 6 is a third. And in this problem, Vn, I'm saying that the amplitude of it is 12. So I'll say that V1 star is equal to 12 times a third, which means that V1 star is equal to 4. V1 star is equal to 4. Now, what's nice about that is I just found up here that the original V1 star, this is 4. This is 4 volts across that transformer on the left. And now I can go ahead and find V2 star. Based on this ratio here, and what we discussed, if the left side is 4, the right side has to be 8. Because if I were to do 4 to V2 star is equal to 1 to 2, we see that 4 over V2 star is a half. That means that V2 star has to be 8. So let me go ahead and I'm going to copy this down. Let's copy that. So that means that now this V2 star is 8 volts. So now that I have 8 volts as being essentially the source on my right side of my circuit, we will go ahead and do voltage division again, because now I want to find V out. V out will be the 8 volts over 6 divided by 6 plus 2. That's our voltage division. That's 6 over the sum of those impedances in series. This would be 8 times 6 over 8, which means that our V out just ends up being 6 volts. And that's our answer for this problem. The general idea of transformers is that using those rules with the ratio of voltages, the fact that power is conserved, understanding how to transform an impedance over from one side to the other, you can solve most circuits that have a transformer in it, as long as you are keeping track of what is what and trying your best to simplify the circuit as much as possible. If you have any questions, please let me know. Hopefully this was helpful. And that's it. Thanks for watching. Bye.